Hello everyone, this is Dr. Ross and I'm about to make a short video on some basic lab skills, and this video will be about precision and accuracy in the lab. So let's go. I'm going to share my screen and then I'll start writing some notes down. Okay, so hopefully everyone can see my screen now. Okay, so precision. Essentially, precision is a student's reproducibility in the lab. So if a scientist were to do an experiment once, that's great. But if you can do the same experiment again and again and again and achieve the same result, it adds credence to those results, and that would mean that you have a high level of precision. So let's see. So a student's precision in lab is their reproducibility. Reproducibility is not spelled with a P. Reproducibility starts with an R. Reproducibility. Okay. There's different ways that we can look at precision though. So let's start with absolute deviation. Absolute deviation, which I'm going to represent as a D, the modulus of D, or the absolute value of D. So this is the first type of precision that we'll look at. So take two measurements, A and B, and let the average be X. So take two measurements, A and B, and then let the average be X. Okay, I'm just going to scroll down so I've got some more space. Let their average be X. So then the absolute deviation is the difference between A and B. So the absolute deviation is the difference absolutely between A and B. Or it would make sense in another context to have absolute deviation is the difference between the average and A, if you're looking at the absolute deviation of A, or the absolute deviation of B. So let's call this A, B. That would be the absolute difference between the average and B. So within the context of what you're looking for, there are different subtle ways, not so subtle, but slightly different ways that you can phrase absolute deviation. In terms of units, absolute deviation has units of the measured value. So let's put units. So D has units of the measured value. Units of the measured value of A and B. Not or B, but and B. Okay. So we can clearly see that because you've just got a subtraction, A minus B or X minus A or X minus B, it's going to be one unit minus the same unit, which is going to give you a value in that unit. Absolute deviation has to be positive because it's an absolute value. So it wouldn't make sense to consider any negative values because they don't exist. Okay, we've got a little bit more space. Let's start talking about relative deviation. So we've had a look at absolute deviation. Let's look at relative deviation. And relative deviation, we're going to talk about as either percent relative deviation or parts per thousand relative deviation. And this is the symbol for, instead of percentage being 1 over 100, 1 over 1,000 or parts per thousand would be written like this. So we'll look at these two. Okay, so take two measurements, A and B, and let the average be X. Take two measurements, A and B. Let the average be X. So exactly the same as earlier. Then the percent relative deviation is just the absolute deviation from our initial part of our video divided by A times 100%. So that would be the relative deviation in A, or let's use our space a bit more wisely. Or, so this would be the relative deviation of A. The percent relative deviation of B would be the absolute deviation of B over B times 100%. Or you could have the percent relative deviation of A or B compared to the mean would just be, so I'll leave the label blank here, but the absolute deviation over the mean as 100%. Okay, one more just to give you an idea of what the parts per thousand relative deviation would be. So I'll write it here. We could have parts per thousand relative deviation of A, for example, is just the absolute deviation of A over A by 1,000. Okay. Let's talk about units and then we'll compare and contrast absolute deviation from relative deviation. Relative deviation has no units. So let's look at units real quick. Relative deviation has no units. And that's because you have this fraction. So the numerator and the denominator both have the same units, so the units cancel, and then you scale by a number which has no units. So overall, relative deviation has no units. Relative deviation can be positive or negative. Or negative. And that's because although the numerator has an absolute value, the denominator does not. No, it can't be negative, can it? It can just be very small. So let's see. Eraser. Eraser. Immediately erase. Can only be positive. That I'm thinking while I'm recording this, that makes sense, right? So if the numerator is smaller, yeah, it just multiply and divide, so you can't have a negative number yet. So relative deviation can only be positive. Okay, before, let's see. Yeah, so before we move on to our third type of precision, let's just quickly compare and contrast the absolute deviation from the relative deviation. The absolute deviation is good if you just want to compare one data point with another. It's good for seeing if you have an outlier, but it really doesn't tell you whether your data is good. You know, what is a reasonable deviation in any given set of data? Is a 1% deviation good? Is a 5% deviation in one circumstance better than a 0.5% deviation in another circumstance? There's no context in absolute deviation. In contrast, if you look at the relative deviation, it adds the context relative to what the value is. So if you've got a very large value and a very small deviation, that's good, and that's accounted for in relative deviation. On the other hand, if you have a very small value and a proportionately large deviation, that would also be accommodated in the relative deviation, and it would return a large percent relative deviation. So relative deviation can tell you if your deviation is good compared to the measurement it's purporting to report against. Okay, that was a mouthful. Okay, let's look at our final topic in precision, which is percent relative average deviation from the mean. So let's underline that. So this is going to be percent relative average deviation from the mean. And I'm going to call that either percent rad, relative average deviation, or you can have parts per thousand rad. Take three measurements. Take three measurements. Let's call them A, B, and C. Let the average be X. Let the average be X. Let's scroll down to make some more space. So let the average be X. Let the absolute deviation be exactly as we've stated earlier. So let the absolute deviation, for example, of A equal the average X minus A, or the absolute difference between the mean and A. Let the absolute deviation of B equal the absolute difference between A and B. And let the absolute deviation of C equal the absolute difference between the average and C. Okay. Let the average absolute deviation, so let the average absolute deviation equal D with a bar on top. So here the average I'm symbolizing as this bar. Where the average absolute deviation is going to be the absolute deviation of A plus the absolute deviation of B plus the absolute deviation of C, in this case divided by 3. So just the mean. Given all of that, then the percent relative average deviation from the mean is going to be the average absolute deviation divided by the mean by 100%, and the parts per thousand relative average deviation from the mean is going to be the average absolute deviation divided by x, which is the average, by 1,000. Okay. The relative average deviation from the mean, so going from absolute deviation to relative deviation to relative absolute deviation from the mean, relative average deviation from the mean, it just gets more and more context embedded. It just gets more context embedded. For my students, so I'm uploading this to a video sharing platform, but for my students, I have the lab skills document, which will have examples of these topics built in. So to keep this video short and sweet, that's all I was going to say about precision. I have a couple of things to say about accuracy. So we can start to talk about accuracy right now. So just have one final page to talk about accuracy. Okay, accuracy. So what do we mean by accuracy? A student's accuracy in lab is their ability to measure a known value. So a student's accuracy in a lab environment is their ability to measure a known value. So as you can appreciate, this is important. So your lab skill in any chemistry lab course should incorporate your, how good are you in the lab? So if you're asked to measure something and you can accurately measure it, that should be reflected in your grade. If you can't, that should be reflected in your grade. If you can do it once and never again, your precision, that should be reflected in your grade. So, okay. Absolute error. So analogous to absolute precision, we can look at absolute error. Which I'll call AE. So for measurement A, for a measurement A, the absolute error of A is the absolute difference between the measurement and the true value, where C is the correct, or typically what's known as the accepted value. Okay, so completely analogous to absolute deviation, but instead of you looking at one data point and another, or one data point and the mean, you're looking at one data point and a benchmark standard that you're comparing it to. Absolute error has units of the measured value. So units, AE has units of the measured value. And it's going to be positive, only positive values, because there's an absolute value there. Okay, let's compare that with relative accuracy, which would be our last topic in this video. So relative accuracy. Which we will call RA. We can have percent relative accuracy, which is the absolute error divided by the true accepted value as a percentage. Or we could have the parts per thousand relative accuracy, which is the absolute error over the true and accepted value as 1,000. And relative accuracy has no units. Relative accuracy has no units for the same reason that the relative precision had no units, relative deviation, because you have a fraction, the numerator and denominator both have the same units. So the units cancel, and then you scale by either 100 or 1,000, which has no units. Okay, so the take-home message, and we'll wrap this video up. So let's go to the take-home message. Take-home message. In lab, scientists need to optimize accuracy and precision. I'll keep it vague like that. So not only the accuracy and precision of data, but also the accuracy and precision of one's ability to acquire the data. So we want to inspect data for its level of accuracy and precision. The lower the accuracy and precision, the less credence we should place in that data. And that will wrap up this video, and I hope it was useful.